Okay, I think this is good. So, hello everyone, and welcome to this junior researcher webinar. Thank you for being here today for this webinar dedicated to exceptional points and observable effects in nuclear phenomena. This webinar will be presented by David Cardona, who is a PhD student at GANIL. And so, David, the floor is yours.
Thank you very much, Lou. So thank you everyone for coming. I will talk to you about exceptional points and the effects that they have in different nuclear observables of interest. So here's a short outline of my talk. I will show you what are exceptional points and some of their characteristics. I will then show you some experiments that have been done in other areas of physics about exceptional points. Then I will give you a short motivation of why exceptional points should be taken into account in nuclear physics. After that, I will give you a short introduction on the Gamow Shell Model in its different representations. And in the end, I will show you how we have used the Gamow Shell Model in the coupled channel representation to study exceptional points in different nuclei. So first of all, what is an exceptional point? An exceptional point is a type of non-Hermitian degeneracy where one can find a set of parameters in a non-Hermitian Hamiltonian for which two or more of its eigenvalues coalesce, while their corresponding eigenvectors turn equal, identical, and self-orthogonal, leaving the Hamiltonian defective or non-diagonalizable. It is this non-diagonalizability that endows its corresponding energy surfaces with very interesting and counterintuitive properties. It is in a stark contrast with the usual Hermitian degeneracies called diabolic points, since in the case of diabolic points, the eigenvalues are degenerate, but the eigenvectors remain orthogonal and still span the full space. Here I have a little illustrative example of an exceptional point in a 2x2 model, 2x2 matrix model. So we have a Hamiltonian with two states which have an interaction due to a shared environment, for example. If we try to find the eigenvalues of this matrix and we want to make its eigenvalues coalesce, we need this square root to be 0. In order to have this square root be 0, since we are dealing with the addition of two square quantities, we need the interaction or any of the parameters to be complex, which renders our Hamiltonian to be non-Hermitian. Here on the right-hand side, we have a little example of how an exceptional point evolves, where the energies and the widths of the states coalesce into the same point. And here in the lower part, we have the well-known case of the Hermitian avoided crossing. It is the behavior of this square root with a complex argument, which gives the exceptional points and the energy surfaces related to it a rich topology, which also affects the behavior of its corresponding wave functions. Here we have an example of the energy surfaces of the around an exceptional point and around a diabolic point. When we have a diabolic point and we do a loop around it in parameter space, we see that since we are looping around a cone, we end up at the same position after one loop, but we pick up the famous geometric Berry phase. In contrast, when we loop around an exceptional point, since in this case our surfaces are two Riemann sheets that meet with each other, this loop doesn't leave us at the same starting point after one single loop. We have, in this case, an interchange of the states while also picking up the geometric vary phase. So for this system to go back to the same starting point, we need instead two loops. Now, this may sound something purely like a mathematical game, but since non-Hermitian Hamiltonians have been very successful in the description of open systems, and since open systems are ubiquitous in physics, it means that exceptional points have been studied in many areas, such as optics, microwave cavities, atomic and molecular physics, and even some sensing applications and nuclear physics. One example in which exceptional points have been studied was the first experimental observation of them. In this case, this group used a couple of microwave resonators coupled to each other. These resonators obey an equation which is analogous to the Schrödinger equation. They have a couple of control parameters, namely the shape of the resonator cavity and a scatterer inside, which provides with the needed absorption to turn the system non-Hermitian. Now, what they did is that they used these control parameters to look at the behavior of the resonance frequency and widths. They found that the frequencies and widths were crossing, which is a signature of having an exceptional point. And then, knowing that there is an exception, some type of degeneracy, they took these parameters to loop around this point. And so what happened with the field inside. So they started with some starting field, they do a single loop, and they land at a very different field, showing that they indeed have seen this non-trivial topology of an exceptional point. So they found something that is not a normal degeneracy. In a more recent experiment, a group used a cloud of cold rubidium atoms trapped in a magneto-optical trap. They drive these atoms to Rydberg states by using some lasers, and then they looked at the transmission spectrum of these atoms. What they found is that for low intensity, low power of these lasers, very few atoms would reach the Rydberg state. So there will be very few interactions among them, and the system would remain Hermitian. So in this case, they will have only one single transmission peak, as we can see here. Now, when they increase this laser power, more and more atoms would reach the Rydberg state, which induced many interactions among the atoms, and this interaction introduced a dissipative channel, which made the system now non-Hermitian. The point where the system turns from Hermitian to non-Hermitian is exactly an exceptional point, which we can see here from the spectrum, where it splits into two with the characteristic square root behavior that I've talked before, which also can be seen from the transmission peaks, where the single peak splits into two. Another thing that they did to further prove that they have found an exceptional point in this case is to vary the intensity of the laser up and down, and they found that the transmission would follow an hysteresis curve. So the path followed by the transmission would lead to a different outcome if going up and down, showing that they are also looking at the non-trivial topology of an exceptional point in this case. Since we are dealing with the realm of non-Hermitian quantum mechanics, there are some caveats that we have to take into account. So first of all, the Hamiltonian is no longer equal to its Hermitian conjugate, and also the energy is now complex. So now the brass and the kets do not correspond to the same eigenvalue, and then the usual inner product makes no sense in a non-Hermitian setting. Now we will have to use something called the bi-orthogonal normalization, which relies on left and right eigenvectors to replace the scalar product. With this, I can introduce a very important quantity called the rigidity, the phase rigidity. This is simply the ratio between the non-Hermitian and the Hermitian scalar product. It gives us a measure of how important the non-Hermitian effects are in a given system. So it is 1 for well-separated states, so there are no non-Hermitian effects going on, and then it turns to 0 at the exceptional point where the state has become self-orthogonal. In this region, we have maximal non-Hermitian effects. One of the other main consequences of the self-orthogonality is what happens to the expectation values of operators. Since the expectation value depends on the norm of the wave function, as the wave function approaches the exceptional point, this starts going to 0, the denominator starts going to 0, and the expectation value becomes more and more sensitive to parameter changes until it diverges at the exceptional point. Now, why should we study exceptional points in nuclear physics? Well, first of all, nuclear physics provides a natural setting for the study of exotic resonance phenomena, since it naturally bridges several regimes of binding from discrete states to the scattering continuum, while also spanning a very wide range of resonance lifetimes. We have very narrow states and very broad states. So the study of exceptional points is relevant in nuclear physics, since their existence brings many of the assumptions that the conventional tools of nuclear physics use in reaction theory, like, for example, the hermiticity and the simple poles of the S matrix in the R matrix theory. It also breaks the ansatz of Laurentian shapes, and also the non-degeneracy of the states in distorted wave approaches. So we need a theory that can handle all of these issues. This theory that we have chosen is the Gamow Shell Model, which treats the continuum exactly and can naturally accommodate all of the features of exceptional points. Now, the standard shell model has been very successful in the study of bound nuclei close to the valley of stability. But once we start moving towards the drip lines or above particle emission thresholds, the nuclear states start being embedded in an environment of interconnected web of nuclear states with its neighboring nuclei, meaning that it is in fact an open quantum system. The Gamow Shell model allows the study of nuclei as an open quantum system by not only using bound states in its completeness relation, like in the standard shell model, but it extends it to the complex energy plane by allowing to have also resonance and scattering states. These are included through the Bergen completeness relation. This single particle relation can be used now to construct a many-body completeness relation through Slater determinants built from all of these types of states, bound, resonant, and scattering. And then we can use this many-body completeness relation to expand any many-body state we want in this basis. Having that, we can now plug our many-body wave function into the standard shell model Hamiltonian, and we obtain whatever solution we want for the shell model. In this case, since we have included resonant and scattering poles, we have to pay a price. This price is that the matrix representation is now complex symmetric, so non-Hermitian, which is exactly what we wanted for the study of exceptional points. Given that we are working with a complex symmetric matrix, diagonalization now yields complex eigenvalues. These complex eigenvalues also affect the behavior of expectation values for operators, which are now complex as well. In this case, the real part is the mean value of the observable, while the imaginary part is some sort of intrinsic uncertainty in a similar vein to the width of the states. Now, the Slater determinant representation does not have clear channel asymptotics, since the Slater determinant doesn't allow us to choose what are the incoming and outgoing channels. So we cannot study reaction observables with this representation, but it is the prime tool for the study of structure of nuclei in all regimes of binding. If we want to now study reaction observables, we have to turn to another representation of the Gamow Shell model, which is the coupled channels representation. In this case, the wave function is expanded as a sum of channel wave functions, which are binary. These channel wave functions are constructed as a product of target and projectile wave functions built from the Gamow Shell model in the Slater determinant representation, so we can still keep all of the advantages of being in an open quantum system framework. Then we just plug this wave function into the Schrodinger equation. We obtain the coupled channels equations. Which can then be solved, and through asymptotic matching of the wave functions, we can obtain DS matrix, which allow us now to study or calculate all different reaction observables that we may need, like the differential convection and so on. So in the following, I will show you the results that we have obtained with the use of the Gamow Shell model in the coupled channel representation to study exceptional points and their effects that they have in different quantities of interest. For this, we have chosen different nuclei that have a very specific characteristic, which their spectrum must contain a doublet of states with the same parity and angular momentum, which have a different variety of closeness among them and different widths. It is, of course, understandable that if they are close to each other, they may be close to an exceptional point, which is the coalescence of these two states. Now, in the case of lithium-6, we have used a Hamiltonian, which is composed of a one-body potential with a Wood-Saxon spin orbit and Coulomb term, and also a two-body interaction with of the FHT type with a central spin orbit tensor and Coulomb terms. The channel basis is composed of three mass partitions, so helium-4 plus neutron, helium-5 plus proton, and lithium-5 plus neutron. In the from now on, the parameter that we have used as control parameter to find the exceptional point is the L=1 part of the one-body spin orbit for protons and neutrons. Here we can observe that the spectrum is how the spectrum is modified with the exceptional point that we have found. The exceptional point is in between the two experimental states and is just below the protons threshold, meaning that it has only one open channel. This fact is important for the characterization of some of the effects that the exceptional point may have on some observables. So here we can see the evolution of the energies and the partial widths of these two states when approaching the exceptional point as a function of the control parameters. We see that they indeed show the square root behavior characteristic of an exceptional point. Here also in the partial widths, we can see the closing of the proton channel and the coalescence of the deuteron channel to partial widths to the same point, meaning that we have the exact same wave function for both states. On the right-hand side, we have the rigidity. Throughout most of the evolution, the rigidity is very, very close to 1. So at the starting point, we can expect very little non-Hermitian effects until it very quickly decays to 0, where we have the exceptional point and maximal non-Hermitian effects. This is exemplified here in the calculation of the spectroscopic factors as a function of the control parameters again when approaching the exceptional point. We can see that in the beginning, when the rigidity is very close to 1, these quantities vary very little and are almost constant. But then as we approach this region of decaying rigidity, they start to vary very wildly until they diverge exactly at the exceptional point. But if we look at the sum of these two resonances throughout the whole evolution, we see that their divergences cancel exactly, and the whole evolution remains continuous and finite, meaning that even though we have lost one state at the exceptional point, this two-dimensional subspace that they span stays physically meaningful and useful, even though they have lost all of their individuality. Another way of looking at an exceptional point is as a double pole of the S matrix. So from this, we can obtain also what are the effects of exceptional points in reaction observables. Here we have the elastic cross-section for deuteron. At the starting point, we have two very different peaks associated with each of the resonance. Now, if we look at the expression for the S matrix for a double pole with a single coupled to a single channel, and we plug it into the usual expression for the elastic cross-section, we see that the elastic cross-section gives us something that looks like a Breit-Wigner peak, as we expect, but multiplied by an interference term that vanishes exactly at the exceptional point, which is exactly what we see from our calculation. So even though we have lost one of our states, there is still some kind of imprint of having two of them. We have here not two peaks, but in reality, one split peak. Another signature of exceptional points in reaction observables is in the phase shift. It is well known that for a single resonance, the phase shift has a change of pi. But for an exceptional point, instead, we have a shift of 2 pi. Again, we have just one single state, but this looks like two states on top of each other. So they still leave some imprint behind for us to see. If we want to continue looking at the dynamical effects on resonances of exceptional points, we can see what happens to the survival probability. The survival probability is defined as the probability that a prepared state at t0 at time 0 has not decayed yet. This quantity is also related to the so-called spectral function, which gives us the pole energy distribution of our resonance. It has been known for a long time that the pure exponential decay is not possible due to different factors like the existence of a lower bound in the energy spectrum and deviations from the Breit-Wigner shape in the spectral function. So here, from our calculation, we see the three expected regimes of decay. We have a pre-exponential zone, which depends on the preparation of the state. We then have an exponential decay, which is characterized by the width of the resonance, which is governed by the most important poles in this energy distribution. And then in the end, we have a power law part, which comes from the fact that we have this energy cut due to the threshold, which also depends on the angular momentum of our corresponding state. Now, since the exponential intermediate zone depends on the characteristics of the poles, one can expect that having a double pole will have some effects even on this region. Here we have calculated the survival probability for the state related to the exceptional point. We still have three distinct regions, but if we look at the intermediate times where we are supposed to see exponential decay, having a closer look, we see that it is no longer purely exponential there either. There is a parabolic envelope multiplying the exponential. So here we no longer have any exponential decay in any regime of time. Moving on to the next case, we have beryllium-7. Here we have studied the phi-half doublet that is on top of the proton and helium-3 thresholds. We see here that the exceptional point lands again in between the two states. This nucleus was modeled using a Hamiltonian with the same components as before, but with a channel composition of three mass partitions of helium-4 plus helium-3, lithium-5 plus deuteron, and lithium-6 plus proton. As I told you before, it is important to note that now our exceptional point state has two available open channels. Here again, we can see the evolution of the energies and the widths when approaching the exceptional point. We see again the square root behavior around it. We also see the behavior of the partial widths, which we can see that they independently coalesce to the same value, meaning that we have the exact same wave function for both of the states. Here in the rigidity, we can see that even at the start of the evolution, the rigidity differs from 1, so we can expect to have some non-Hermitian effects from the get-go. This is also seen from the behavior of the spectral function. We see that at the starting point, the spectral functions are already overlapping, so we can expect some effects from this overlap. And then as the rigidity starts to decay to 0, they coalesce into the same shape until they are identical, and we have again exactly the same wave function. So if we look, for example, at some observables like this transition probability, we see that even from the start of the evolution, we have some values that are not physical, and also we have very wild changes for the expectation values as a function of the closeness between the states. Again, if we do the same addition process as with the spectroscopic factors in lithium-6, we see that the divergences perfectly cancel each other out, and the evolution of this quantity remains almost constant and physically meaningful. So in this case, it wouldn't make sense to treat these two resonances as two independent entities, but as a single intertwined entity. So we have physically meaningful effects and results. Finally, for beryllium-7, we can see what are the effects on its survival probability for the exceptional point state. We see here something that looks like exponential decay, but from a fit, we can see that its width doesn't match exactly the width of the state of the exceptional point. Having a closer look again, we see that this exponential region is also modified by another polynomial, in this case of degree 1, which we guess is probably due to having a second open channel. Another effect of having two open channels for our exceptional point is what happens to the reaction cross-sections, the elastic cross-sections. So we can see that we have for both channels a very similar expression as before, but in this case, instead of vanishing at the exceptional point, we have an extra term which depends on the partial width of the other state. And it is the ratio between the partial widths which would define which of the channels has which kind of effect. So for the helium-3 reaction, we see that we still have the split peak, and we have an enhancement of the peaks, just like with lithium-6. While the proton channel doesn't show any split peak, and we have a suppression instead of the cross section. Finally, I will talk about beryllium-8, specifically this 2+ doublet, since it has long been thought to be one of the prime examples of having an exceptional point lying close by, since these two resonances lie very close to each other and have very similar widths. So one would expect that the coalescence wouldn't take much effort. But as we can see here, the exceptional point doesn't land exactly in the middle, but lands 1 MeV above the two states, above the proton threshold. Here, this beryllium-8 again has been modeled using a similar Hamiltonian as before, with these following mass partitions of alpha-alpha, lithium-6 plus neutron, lithium-7 plus proton, beryllium-7 plus neutron. As we can see here, from the evolution of the energy and the width, we indeed have found an exceptional point, but we can see that its coalescence is very, very sharp. We can also see that the evolution of the rigidity remains very strongly one along most of the evolution, up until a very narrow parameter range where it goes to 0, which is where we find the exceptional point. It is well known that these two states have a very different structure, and we suggest that this structural orthogonality of these two states is what makes the exceptional point to be difficult to find for this case. And it was then necessary to have a structural change, which was driven by the crossing of the proton's threshold, as we can see here from the evolution of the partial widths, where once they cross the proton's threshold, one state remains purely alpha and the other one purely proton, until they meet at the exceptional point and separate back again. So in the end, I have shown you that the exceptional points can be indeed found in realistic nuclear physics calculations. I have shown you that they leave very clear imprints in many observables of interest in nuclear physics. Exceptional points represent the extreme case of configuration mixing, since at the exceptional point they lose completely their individuality, and it has very big observable consequences. And also, they must be taken into account in experimental studies where we may encounter close lying resonances with the same angular momentum and parity, which we may have some issues with its analysis with the standard modes of data analysis. Thank you very much.